Good morning, friends. It gives me immense pleasure to be here again for my course, Engineering Thermodynamics. As of now, I have covered in this module power cycles. First one, Otto cycle. Second one, diesel cycle. Third one is dual cycle. The concept and theory behind the dual cycle I have already covered. I have done my derivation for the dual cycle for the efficiency and also work done with all the state points of the processes. And as you know that in the dual cycle we have combination of Otto cycle and the diesel cycle. The heat addition, if you see first 1 and 2 is a compression. 1 and 2 is a compression, and then 2 to 3 is constant volume heat addition, and then 3 to 4 is constant pressure heat addition. 4 to 1 is adiabatic or isentropic expansion, and 5 to 1 is constant volume heat rejection. So these are the processes which we have done, and the state point 1, 2, 3, 4 and 5 we have already calculated, and how to find mathematical expression we have already done. Now today I am going to discuss about this cycle, the efficiency of this cycle, and how we can proceed ahead with this. So here we have the one numerical, and this numerical is related to the dual cycle. And so this is the problem statement for this cycle. The swept volume of a dual cycle engine is 0.0053 meter cube, and the clearance volume is 0.00035 meter cube. The maximum pressure is 65 bar. Fuel injection ends at 5% of the stroke. The temperature and the pressure at the start of the compression are 80 degrees centigrade and 0.9 bar. Take the gamma is equal to 1.4 for air. So we have to find the temperature and pressure at each point, work done, and the air standard efficiency of the dual cycle. So first we should understand what is the concept and how we can go ahead with this problem. So I will just draw one rough PV diagram. So in this you can see that this is the starting point 1, then this is the 2 compression, 2 to 3 is isochoric heat addition, 3 to 4 is isobaric heat addition, then this is the 4 to 5 is expansion, and 5 to 1 is heat rejection. So the state point 1, that is P1, is 0.9 bar, and T1 is 80 degrees centigrade is given. The volume, the swept volume. So what is the swept volume? This we can see from here. So if this is the piston, this is the piston here, and if it is coming up to here, this is your clearance volume. Clearance volume, and from here to here, from this point to this point, this is the Vs or a swept volume. This is also called as a stroke volume. So from here to here, this is V1, and this is V1 is equal to V5, and here V2 is equal to V3, and here is V4. So V4 is given here. So here if you see V1 means the full volume from here to here, total volume is equal to stroke volume plus clearance volume. And this he has given fuel, the fuel injection ends at 5% of the stroke volume. So means V4 minus V3 is equal to 0.05% of the Vs. This is given by this. That we have to take care, and we will proceed ahead with the solution of this problem. From the, if you see the problem here, the cycle is a dual cycle. This is mentioned here. The cycle is a dual cycle. So first thing we have to see that the cycle is dual cycle, and the swept volume Vs is equal to 0.0053 meter cube, and the clearance volume is given as 0.00035 meter cube. The maximum pressure is equal to 65 bar. So what is the maximum pressure? Again I will draw here. How we will determine it? Which one is the maximum pressure? So 1 to 2, 2 to 3, 3 to 4. So 1, 2, 3 and 4. So this is the point, and this is the point where you have the maximum pressure. Because here this is the P and this is the V, PV diagram. In this PV diagram, you can see that here P3 is equal to P4 is equal to P maximum. So here we can write that P maximum is given 65 bar. This shows that it is a P3 and this is also P4. And this is given as a 65 bar into 10 to the power 5 Newton per meter square. And this is a P3 is equal to P4. Now the fuel injection ends at 5% of stroke volume. So here T1 is equal to 80 degrees centigrade plus 273. This is 353 Kelvin. T1 is equal to 0.9 bar. 0.9 into 10 to the power 5 Newton per meter square, and gamma is equal to 1.4. If this is not given also, and it is air standard cycle, we have to use this index as a 1.4. So we have to find out the each state points. P1, V1 is given. So state points are P2, V2, P3, V3, P4, V4, P5, V5. These all points we have to find out. Okay. So that is the meaning of state points. Also we have to find out the work done. And if we find this is first we have to find, the second this one, and third this one we can get by this method. Now we have to draw the process in PV and TS diagram, pressure and the volume diagram, and temperature and entropy diagram. This will be very good to visualize the thing, what type of processes we are following. So here if you see in PV diagram, the 1, 2 is a S is equal to constant and it is a compression. So and this is engine, so it is moving in a clockwise direction. So 1 and 2 is a isentropic compression or reversible adiabatic compression. In this case, you see P1 is this much and now P2. So pressure is increased from P1 to P2, and if you see this TS diagram from here, temperature is increased from T1 to T2. It is increased. So by this compression process, when the piston is moving from bottom dead center to the top dead center towards the front of the cylinder, it is compression is taking place, and in this compression process, pressure and temperature both are increased. Now, if we see the next process is 2-3. This 2-3 is a isochoric heat addition or constant volume heat addition. Here, if you see V3 is equal to V2, and if you see here V1 is equal to V5, and here is this is the V4. Okay, so 2 to 3 is a heat addition. We are adding the heat here at a constant volume, and also we are adding the heat from 3 to 4. So it is a constant pressure process. So 2 to 3 is a constant volume heat addition. 3 to 4 is a constant pressure heat addition. So what is the difference? 2 to 3, if you see in the TS diagram, the slope of this 2 to 3 is much more than the slope of this constant pressure cycle. So here if you see, this is volume is constant, 2, 3, V is a constant, and 3 to 4, P is a constant. And if you see the slope of this, so slope of volume curve is much more than the slope of the constant pressure curve, which is depicted in this system. So here if you see, it is a constant volume, 2 to 3 is a constant volume, and 3 to 4 is a constant pressure process. And in this, fuel is injected, fuel is burned, and this fuel is used for the further expansion process. And this expansion process, we get the power. We get the work done in expansion process only. In expansion process, pressure and the temperature will reduce. Just you can see from 4 to 5. Here, pressure is 4 and now pressure is 5. So, the pressure is decreased from T4 to T5 and temperature is decreased from T4 to T5. I have shown in the different colors. So, here at 4 you have the high temperature and high pressure. At the 5 you have less than the 4, and from 5 to 1 heat is rejected, and this you can see the blue line, the temperature is further falling and it is reaching to its initial state. So your cycle is completed. That is why they are called the dual cycle, because here we are adding the Q by constant volume and we are adding heat by constant pressure, and heat is rejected here by Q. In this, heat is rejected. So in this, two systems are there, or two processes are there in which we add the heat, and there is a one process that is called the adiabatic, that is called the constant volume heat rejection, but heat addition is constant pressure and the constant volume, both are there. Now we will solve this problem. Calculation of temperature of all processes. We will go one by one and we will see that how we are going to solve. So if you see the process 1 and 2, this is an isentropic compression process. Here the clearance volume Vc is equal to V2 by V3. So I will draw here so that it will be very much clear that what is the Vc, V2, V3 and Vc and all. Okay, so here this is a constant volume process. Here this is also, so here V1 is equal to V5 and here V2 is equal to V3 and here is your V4. So if we draw here one piston and cylinder, just I am drawing here only, just you can see here. So this is your, here initial your piston is here. This is the piston here and this is called your Vc, that is the clearance volume, and from here to here this is called Vs, stroke volume or the swept volume. So V1 is equal to what? V1 is equal to Vs plus Vc. So here we can see that V2 is equal to V3 is equal to Vc. It is a clearance volume. So this V2 is equal to V3. It is given as 0.00035 meter cube. Swept volume is here. Vs is given 0.0053 meter cube. Cylinder volume, that is Vs plus Vc, and this is equal to V1. So it is given Vs plus Vc. So 0.0035 plus 0.0053, this you will get 0.00565 meter cube. So this is your total volume or the cylinder volume, and this is represented that V cylinder is equal to V1 is equal to 0.00565 meter cube. I think up to here it is very much clear. If you like it, please press the like button and subscribe if you feel so. Now it is always advisable to find the state point. We know the P1 and T1. We have to find P2, T2, T3, T3, P4, T4, and P5, T5. So I will go step by step. First, I will start the process 1, 2. 1, 2 is a isentropic process. So for the relationship of pressure and the volume is equal to P1 V1 to the power gamma is equal to P2 V to the power gamma, or we can write P2 by P1 is equal to V1 by V2 to the power gamma, and this V1 by V2 is equal to RC. RC is a compression ratio. So this compression ratio is what? It is a cylinder volume is V1 from here to here plus the clearance volume VC. So V1 by V2 or VC. V1 we know here 0.00565 and VC we know 0.00035. So here P2 by P1 is equal to RC to the power gamma, and so P2 is equal to P1 RC to the power gamma. We know the P1, we know the RC, we can find out the P2. So P1 is equal to 0.9 into 10 to the power 5 Newton per meter cube, and then 0.00565 it is the V1 and 0.0035 is V2. So we will get here 44.20 into 10 to the power 5 Newton per meter square or Pascal. So this we can write as a 44.2 bar. Now we got the P2 is equal to 44.2 bar. Now we have to find out the temperature of point 2 here. That is the P2 comma T2. Okay, so again the same type of relation between temperature and the volume. Here it was the pressure and the volume. Now temperature and the volume. So here T2 by T1 is equal to V1 by V2 gamma minus 1. So if T and V relations, it is gamma minus 1. If it is the P and V, it is gamma. And if it is T and P, it is gamma minus 1 by gamma. That we have already learned during our previous classes. So here V1 by V2 is equal to RC gamma minus 1, and RC we have find out here 16.14. So here T2 is equal to T1, RC is equal to 16.14, 1.4 minus 1, 0.4. So this calculation will go T2 is equal to 1073.83 Kelvin. So we got the first P2 and T2 we have achieved. So P2 we got 44.2 into 10 to the power 5 Newton per meter square, and T2, these two state points, for the point 2 we have received. Now we will go for the next process, that is the constant volume process. Just I will draw here. What is the meaning of this? This is the 1 and 2. Then this is the 3 and this is the 4. And from here this is the 5. So we have seen that 1 and 2 we got, 2 point we have got. Now we have to find out T3 and P3. This point we have to see. So how? For this we have to use the process 2, 3, and it is a constant volume process. So by using the gas equation, P2 V2 by T2 is equal to P3 V3 by T3, or here is a constant volume, V2 is equal to V3, both are cancelled. So we will get here P2 by T2 is equal to P3 by T3. So T3 is equal to P3 by P2 into T2. P3 is given, P2 we have just find out. It is a maximum pressure. So P3 and P4 is equal to 65 bar. It is given. So now T3 is equal to 65 into 10 to the power 5 divided by 44.2 into 10 to the power 5. It is cancelled. And the T2 we have just now received, obtained 1073.83. So we got the T3 is equal to 1579.16. So if you see here, we got the T3 is equal to 1579.16 and P3 is already given 65 bar. So now we have to find out this point. So here P4 is given. P4 is 65 into 10 to the power 5 Newton per meter square. It is given. We have to find out what is the temperature. So same way for the process 3-4 using the gas equation, P3V3 by T3 is equal to P4V4 by T4, or here P3 is equal to P4, it is a cancel. So here we can write V3 by T3 is equal to V4 by T4, or T4 is equal to V4 by V3 into T3. But here if you see, V3 is equal to V2. That is the clearance volume, and this is given. So now we can see that here to find V4, condition is given in the problem that fuel injection ends at 5% of the stroke volume Vs, which is given as. So here V4, here, this is the V4, V4 minus V3. V4 minus V3, it is given here, and this V4 minus V3 is equal to 5% of the stroke volume. So 5%, 0.05 into here 0.0053. So V4 is equal to 0.05 into 0.0053 plus V3. So here we will get, after the calculation, we will get that V4 is equal to 0.000615 meter cube. So we have got this point. We got here T4 and P4 we have obtained. This point we have obtained, this point we have obtained, this point we have obtained. Now we have to obtain next point V5. So if we get the V5, we will be able to complete all the state points, and that was the first question in which it is asked that find the state point of each process. So we have now obtained that T4 is equal to 2774, and this is the highest temperature. So if in question it is given highest temperature, so it is at 4 point we will have the highest temperature in the dual cycle. That we have to take care of. Now we have to see the 4 to 5, and this 4 to 5 is a one to 2, 2 to 3, 3 to 4, and 4 to 5. 1, 2, 3, 4, 5. This. So this is the isentropic expansion. In this process, the whole work is obtained. So we have to find out what is the temperature of the 5. 4 we have got. We got the 1 also. So from here we can find out that P4 T4 to the power gamma is equal to P5 T5 to the power gamma. So we can find out the P5 is equal to this P5 is equal to P4 V4 to the V4 by V5 to the power gamma. So here we know that V5 is equal to V1. So P4 is equal to V4. This P5 is equal to P4 V4 by V1 to the power gamma. So now here P5 is equal to P4 is equal to 65 into 10 to the power 5, and here V4 is equal to 0.000615 divided by 0.00565 to the power 1.4. So we will get here the P5 is equal to 2.91 into 10 to the power 5 Newton per meter square, or 2.91 bar. So we have received this is equal to 2.91 bar. This is the P5. Now we have to find out the T5. Same way as in the 1-2, we will also find out T5. So we know that by the gas equation, T4 by T5 is equal to V5 by V4 to the power gamma minus 1. V5 is equal to 1 V1. So V1 by V4 to the power gamma minus 1. V1 we know that 0.00565, and the V4 is equal to 0.000615 to the power 1.4 minus 1, and we will get 2.43. So T5 is equal to T4 divided by 2.43. So T4 we have received 2774.81 divided by 2.43. So we got the T5 is equal to 1149.5 Kelvin. So we got this point also. So P5 is equal to 2.91 bar and T5 is equal to 1141.9 Kelvin. So all the state points we have received. These state points are P2 comma T2, P3 comma T3, P4 comma T4, P5 comma T5. These all we have received, and these are the answers which we have. First question is asked that what are the state points. So this we have received. Now we have to further proceed ahead and find out the work done. And we know that from the first law of thermodynamics that heat can be converted to the work and work can be converted to the heat. So that principle we will use here. So del Q is equal to del W. So here we have to find out the how much you are supplying the heat and how much you are rejecting the heat. So the difference between supplying the heat and the rejecting the heat, Q in minus Q out, or QH divided by minus QR is equal to W. This we are going to see here. So work done and the efficiency we have to find out now. So by the first law of thermodynamics, we know that del Q is equal to del W. Heat added is equal to QA is equal to heat added at a constant volume plus heat added at a constant pressure. I will draw a small here PV diagram. It will be easy if we can draw the diagram, and then we have to explain that what is it. So this is the 1, 2, 3. This is here added here. This we can write like this. Okay. So 1, 2, 3, 4, 5. So here heat added is this one at a constant volume. I will write here QV and here is a QP. So here heat added at a constant volume plus heat added at a constant pressure. So MCV T3 minus T2. So heat added at constant volume is what? T3 minus T2. MCV, because it is a constant volume. So we have to take the specific heat at a constant volume and plus this is the constant pressure 3 to 4. So MCP T4 minus T3. If you take the M common, then CV T3 minus T2 plus CP T4 minus T3. So we have written as a equation number 2. Now we have to find out the mass. How much? Because here mass is given, but in question direct mass is not given. But how to find out? So we can find out by the gas equation that P1 V1 is equal to MR T1. So M is equal to P1 V1 by R T1. P1 we know, V1 we know R is a constant 287 for air and T1 is 357. So this pressure, this volume, this is the gas constant and this is the 353 is T1 is given. If you make this all calculation, you will get mass is equal to 0.005 kg. So now we have to put this mass in this equation M. We know the CV, we know the T3, we know the T2, we know the CP, we know T4 and we know the T3. All these temperatures we know. Only M we are not aware, so we have calculated by the help of this. So now we can find out the total heat added. QA is equal to 0.05 in bracket 0.717 1579.16 minus 1073.83 plus 1.005 2774.81 minus 1579.16. So here you will get QA is equal to 7.82 kilojoule. This we got the how much heat is added. So the heat added in the system by the help of injecting the diesel and how much it is burning, this gives the heat of 7.82 kilojoule. That much heat we are supplying. But we have to find out how much heat is rejected. So net work done is QA minus QR is equal to net work done. So we have to find out next how much work or how much heat is rejected. That is the QR. So heat rejected during the process phi1 is equal to QR is equal to MCV T5 minus T1. So what is the T5 and what is the T1? So here I am again drawing a small diagram here. Dual cycle. This is the 5, 4, 3, 2, 1. So here T5 and this is the T1. So T5 minus T1, this is the heat rejected. I am writing here QR and here it is QA. This is the QA. So QR is equal to MCV. It is a constant volume process. We have to use the CV, not the CP. So QR is equal to MCV T5 minus T1. M is given 0.005. CV is 0.717 and T5 is equal to 1151.9 minus 353. If you calculate these all things, you will get the heat rejected is 2.83 kilojoule. This is the heat which is rejected. So now net work done is equal to, by the first law of thermodynamics, QA minus QR. QA we have found out 7.82 kilojoule and QR is here 2.83. You will get 4.99 kilojoule. This is the work done which is produced by this dual cycle engine. So as of now we have got the state point 2, 3, 4, 5. One is already given. We have found out the how much heat is added, how much heat is rejected and how much work is done. Now to find out the efficiency. We know by the definition that efficiency of any cycle, that is eta, is equal to work done divided by heat added. So work done we have find out here W and we have also find out the heat added. W is equal to 4.99 kilojoule and heat added is 7.82 kilojoule. If you divide it, you will get 0.6381. Then you multiply it by 100, you will get in percentage. So efficiency of this dual cycle is 63.81%. It means what? Whatever we have given heat, we have not got the same amount of work. We have got only 63.8. So nearly it is 36%, 36.2%, 36.2% losses are there. That is the indication of second law of thermodynamics. Second law of thermodynamics states that the efficiency will be there. You will not get the full what you are spending. There will be some losses, there will be some other phenomena, there will be entropy losses, and those things are calculated and counted in this efficiency phenomena. So hope you have understood very well, and a very interesting problem, and this will be helpful to solving even for Otto cycle and the diesel cycle problems. If you understand this problem, I hope Otto cycle, diesel cycle and the dual cycle, all the three types of problem you can handle very well. Okay, next I will be discussing about Bell-Coleman cycle. Not Bell-Coleman, I will Breton cycle, and this I have taken the Eunice Senegal, Michael A. Bowles. These are the references which I have referring from this. Also, I am referring some YouTube video channel for this thing. Any questions you are welcome to ask. It will be my pleasure to discuss the problems. Anywhere you feel any correction needed, you are welcome to comment in my comment box, or you can write in this email which is showing. Please do like this channel and subscribe. Thank you very much for the joining. Till then, wait for my next lecture. It is very much likely to come very soon. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.